What I want to teach you guys today is known as ordinary least squares regression, or OLS regression, or regression, or there's probably 15 different names for the stuff. OLS is a good shorthand, ordinary least squares. But generally speaking, this is our introduction to what is commonly referred to also as regression. Let's play a game. Because one of the great things about statistics is becoming a better gambler. Right? So we did the whole expected value of rolling the dice, right? Understanding how you play craps. Let's play a guessing game. I want you to guess how old my wife is. You can't play because you know my wife. And I think you're the only one. Yes. All right. None of you, except for her, have seen or met my wife, correct? You have? No. Oh, that's correct. Yes. Nobody knows her. All right. Keep your mouth shut. Okay. Now, if I were to say, guess how old my wife is, what would be helpful information to you? Well, that's written up. That's written up there. All right. But what would be, if you had zero information at all, and up until this point in the class, if we're trying to guess a number, what is the best number to pick to guess? Depending upon what it is, a measure of central tendency, right? So if you wanted to guess my wife's age, right, you would use something like the mean. Right? Well, what is the mean of all people? According to the CIA, it's 38 and a half years. Okay. Does that mean my wife is 38 and a half years old? No. How old could she be? She could be in her 40s. How old could she be? She could be in her 20s. Right? So we got a range around that value, right? Sound familiar? Right. Because we know this. Because the only thing you're going to leave this class with is how to do this stupid normal curve. Right? Now, if I were to give you one piece of information to guess my wife's age about me, what would it be? Why my age? All right. So if I told you guys that I'm 53 years old, how old do you think my wife is? Okay, how many of you are not, why aren't you objecting to the fact that I just told you that I'm 53 years old? Okay. All right. So if I give you my age, you think that'll tell you my wife's age. Why? So you've already said it. Say it again. Because generally when you marry somebody, you marry them in the same area. Never mind the fact that there was 13 and a half years between my parents, but let's go with that. All right. Because this is what you think the relationship is. This is known as a scatter plot. How good it fit on the screen. This is called a scatter plot. And what you do is you take two values and you graph them together. This down at the bottom is the husband age. Right? This is my age. This is your X variable. This is your independent variable. My wife's age is what you're trying to predict. This is the Y variable or the dependent variable. We're trying to predict. We're trying to explain how old my wife is. And you all believe that knowing where my age is will help you understand what her age is. All right, let's see if I can do this. All right, there we are. That's the dot. So I am 38, I think. My wife, I believe, is 39. Now, if I said I was 53, all right, so here's 55, 4, here's 53, and my wife's still going to be 39, we'd be way out here. That's not an expected answer, right? Somebody tell me why this dot seems strange compared to the first dot. Okay, fancy statistical term. Didn't know if you knew you were using it that way, but it's called an outlier. It's outside of the main grouping. A lot of times, when we think about these groupings, we think about them in terms of like a cloud. I'm not making that part up. People actually refer to this as like a cloud. Before the fake cloud, it's not really a cloud. You're just storing your information on somebody else's computer, by the way. All right. So you have like a data cloud here. And a dot where if I'm 53, that seems outside of the cloud. It seems like it's an outlier, because it is. It's way out there. Look at some of the other outliers. Here we've got a 71-year-old husband with a 56-year-old wife. That looks strange, right? You're like, oh, you and your daughter. No, it's my wife. Right? It just seems a little odd. And then we've got like a 63-year-old woman with a 53-year-old man. A little different. Okay? They're outside of the cloud. This works for us because we've made an assumption about the relationship between a husband's age and a wife's age. We assume two things. One, that they're correlated together. Right? We assume that as a man's age increases or changes, so should a wife's age. Kind of strange, right? Imagine if there was no correlation between age. What would my scatter plot look like if there was no correlation at all? Right? It would be random. Where would the dots be? The dots would be everywhere. Okay? So we'd have 50-year-old men with, well, it only goes down to 30, but a 30-year-old wife. How about an 80-year-old man with a 30-year-old wife? Right? You could have that if there is no correlation. What I've done is when I looked at the textbook these last couple of chapters, it does something that in political science we don't use anymore. It's called ANOVA, analysis of variance. We don't do a lot of ANOVA in political science. It's more of a psychology kind of thing. But ANOVA introduces to you the concept of correlation. And again, it's in a way we don't use in political science anymore. I want to introduce the concept of correlation using ordinary least squares. So that's why we're going to skip a couple chapters. And the way that, for me, correlation makes the most sense is consider that we are expecting movement between two variables, often together at a uniform rate. Right? So if I were to tell you that I'm 45 years old, what would you guess my wife is? 45, 46, right? You wouldn't say, oh, well, you're in your 45, she must be 90. I'm like, oh, big kind of jump there, right? So we assume there's a little bit of a uniformity of rate as we change. But also that when we have change, that they tend to go in the same direction. So as I get older, my wife's, they don't get younger. Which is kind of what my dad did. All right? We assume that they move together. So for correlation, I always like to explain it as you have two independent variables. or excuse me, two variables that you assume are independent. But when you look at them, they actually tend to move together. Right? Is my wife's age dependent on my age? Right? How so? So I'm 38. What rules make me marry a 39-year-old woman?
They don't.
Okay, then. So they are independent, right? Could I marry a 16-year-old girl? Legally I can I? Isn't the age of consent in South Carolina 16?
Age of consent, but you still have to have parental consent in order to...
All right, I could marry a 16-year-old. Fine, if you want to make it creepy, I'll make it marry an 18-year-old. I, at 38, could marry somebody that's 18, correct? I could also marry somebody that's 108, correct? I could, right? It might not last long. I don't know. But I could, right? There's no legal barrier that is prohibiting me from doing so, right? So my age and my wife's age are independent, right? They are completely independent. With correlation, what we're saying is that there's a tendency to move together. So a correlation between two objects, the stronger the correlation, the more that they move together. So if my left hand and my right hand are clasped, and my right hand goes this way, my left hand moves as well. That's a really high amount of correlation. Even if I have low correlation, right, my right hand moves, does my left hand move? You sure? My right hand just moved. Did my left hand move? Yeah, it moved with it. It didn't move exactly with it, but they both moved. That's the weaker levels of correlation. Now, if it was my right hand and her left hand, and I get up to leave and it stays here, we would agree that there's no correlation at all. It looks pretty good on the scatter plot that there is some correlation between a husband's age and a wife's age. How do we know that? Well, it appears that they tend to move together. Okay. As the husband's age increases, what happens to the wife's age? It also increases. This is known as a positive slope or a positive correlation. They're moving together. Not because they have to, right? There is no law that says when you get married, you have to marry somebody that is the exact same age as you. Right? So Joey, how old are you?
22.
He is 22 years old. You can only marry somebody that is 22 right now. What would this chart look like if it were that law that was in place?
X would equal 1.
All right, X and Y would be the same thing. So would we have a cloud? We would just have the line, right? We would just have the exact same, every dot would line up on the line. That's not a relationship that is correlated. That's a relationship that is determined. Your value of X determines your value of Y. And we could change that a little bit. You're only allowed to marry somebody who is 3 years younger than you are. So Y would equal X minus 3. But you would get the same number every single time. this line will just shift a little bit, but it'll still be just a line. Ordinary least squares is really old. It dates back to the first appearance in a published academic paper to 1805. Legendre used it to calculate, of all things, comet orbits. Like Halley's Comet. Okay. I'm not sure if that's what he used to do it, but the idea. So Legendre publishes his paper, and then there's this guy Gauss. And Gauss is like, oh, you guys like this? Oh, that's cool. I did it like 10 years ago. And Gauss comes out and claims that he invented it, but he didn't really use it because it wasn't all that useful. So not only is he saying that this great idea is his, but it's really not all that great of an idea. So Gauss comes out and says, well, I developed this thing. And for years, they argue back and forth about who should be given credit for creating this thing. Legendre wins because it gets referred to, as you use it over and over again, to the term that he used, which is the method of least squares. The method of least squares. Now this format of finding the least or the smallest amount of squares we use in lots of other contexts today. So when you said least squares in 1805, you were only really referring to one thing. But if you were to say least squares today, people would be like, well, which kind of least squares? That's why we call it ordinary least squares, the first method of least squares. The math is easy. You actually have already learned this in high school. Our value of y, so that's my wife's age, is a function of this additive linear expression. And when I say linear, somebody in here is having an awful flashback to high school algebra, or no, geometry, where you're doing like MBX something, and you're like, y equals mx plus b. Yeah, you already learned least squares regression. It's just we're going to make the letters different Greek, and we're going to add another one. Y equals mx plus b. Well, we keep the b. We just give it a subscript. And we write it in a different order. All right? So this was the slope of a line. You had graph paper. Oh, graph paper. And you had to draw your x and your y axis, and there was always that one professor or that one teacher that would like take points off if you didn't put the little arrows on the axes to say that they went forever. You remember that guy? Yeah, I'm not that guy. Of course he was. Usually the coaches are the social studies teachers, but you know, sometimes. The basketball coach was the basketball coach is always the math teacher. All right, or the swim coach. All right, so you've already learned this. But again, it's statistics. We got to put some Greek letters up there. And we're going to order things around a little bit and use subscripts. So for ordinary least squares, what we're doing is we're taking a value of y, our dependent variable, and we're saying that you get y from, well, following the line. So beta 0 is known as the y-intercept. We also call it the constant of an equation, because once you have that number is going to stay the same, right? So it's your constant. Sometimes when people write this equation, they write it as alpha. That's confusing. Why is that confusing, calling the constant alpha? Why should it be confusing? Okay. Because we already have an alpha. What is the alpha? 0.05. It's our decision rule, right? So we kind of already have an alpha. So we'll just ignore that one. We'll just use beta. Okay. Be aware that it's out there, but we're not going to do that. Then we have our beta 1. Now our beta 1 goes with the appropriate value of our x. So beta 1 is also known as a coefficient. In high school, this was your slope. And the slope is the what over the what? Rise over run. You guys are going to have some serious flashbacks later, which is delta y over delta x. Remember that? All right. So you'd have a line, and then you'd draw like a little triangle underneath it, and then you'd count the blocks over, and you'd end up with a fraction. Yeah. So when you're having your flashback, do me a favor, flashback to prom. See? Yeah, suckers. Prom sucks. All right. So we've seen this before, but a couple of new names. Beta because we use the b's, or it's your coefficient. Sometimes we refer to it as your slope coefficient. All right. The last thing that's new to the equation is this little squiggly e. Epsilon. The reason we have to absolutely put that there is because OLS regression is not determined. When you were doing high school geometry and you were finding the slope on a line on a graph, that was determined, right? You had one perfect line on that graph, which for us means that there must be some law that requires you to marry somebody that is your exact age, because we have a perfect line. But our data is more cloudy. We've got dots everywhere. The reason the dots are everywhere is because of that error term. It's also known as a residual. You want to sound super smart? Throw around the word stochastic. If something is stochastic, it has this randomness to it. Life is stochastic, which means it's not determined. There's a randomness to it. So we've got our equation. I'm going to change y in a couple of ways. I got two different y's. One is y hat. Yeah, we call it y hat because you put a little carroty hat on top of it. Y hat is when you use that equation to predict a value of y. The y that comes out of it, that's y hat. Y bar is just like our x bar. It's the mean value of y. So what's the mean value of wives' ages according to the CIA?
38.
Okay. Okay. So let's skip ahead. And I want to show you what this looks like. So if you were, at the very beginning of this game, asked to guess my wife's age, and you had no information about me, you would just go ahead and you would guess y bar. Now y bar is a constant You would guess that regardless of whatever number I told you how old I was, because I didn't give you that piece of information yet, and you didn't have a theory about how age correlates between spouses. So if I were to say, you know, somebody guess the age of a guy by the name of Charles Jones, and you've never seen Charles Jones or met Charles Jones or heard of Charles Jones, if you're smart, you guess 38 and a half. And that's the guess for any list of names that I give you, because that's the expected outcome, right? That's our measure of central tendency. Has the most area under it in the curve. Okay. But what we're trying to do when we have a data set like, let's go back, like this, and we have a theory, we're going to fit a line onto this data. And if we have the best line, well, that'll give us the best guess. All right, here we go. Let's do a line. Okay, I got a lot here. I gotta get these pots up here. There we go. That's my line. That's my best guess. I have all of this data, and my theory is that all I need to do is if you give me a husband's age, I'll have an equation to spit out a wife's age. Who's traditionally older, wives or husbands? By about how much? Year 2? Can we just say 2? If we say that there's continually a gap between the ages, that's your constant. Okay. Now, what do we think the slope is of this line? Well, as x increases by 1, what do we think happens to y? So we think that beta 1 equals 1.0. Okay. So if I tell you that Charles Jones is 50 years old, what's our guess for his wife? He's 50. Wife's 48, because I forgot to put the negative sign up there. What did you do? You substituted in 50 times 1 with a negative 2. That's what you did, right? What did you forget? Yeah, the little, that's not an ampersand, that's an epsilon. That's our error term, right? What do we do about our error term? We just assume it's 0. Because we have to be aware of its existence, because life is stochastic. There's randomness built in everywhere. Which explains why my dad was 13 years older than my mom. But yet only 1 year older than his first wife.
We just randomly select the 2 difference?
Yeah, because I had to come up with an example of a constant.
So in a question, tell us what that would be?
Yeah, or you can figure it out. Okay. So we've talked about beta. We know what beta is. Beta is our slope. We have years of high school experience finding slopes on graph papers. Whether or not beta is positive or negative determines the direction of the slope. Which again, you learned this in high school. Yes, you did. What happens if there's a zero slope? Yeah, it's absolutely flat. So would husband's age be a good predictor of wife's age? No, it would tell you absolutely nothing. That's like the hands on different people. There's zero relationship between the two. Because one hand goes upstairs to the third floor and the other hand goes off to the library. Because there's zero relationship. There's no correlation. So are we starting to get the feeling that this beta thing is a measure of correlation? If not, I just told you. It's a measure of correlation. It tells you what direction they go, whether they go in the same direction or the opposite direction. And it also tells you how far do they go together. How interlocked are they? Okay, you're going to hate me. But just for a second until you realize I can do this. Right? Because this is nothing hard. How are we going to find beta? Let's make this a big B. Well, just stay with me here. Take a look at it. We've got the sum of our observed versus the mean for both variables, multiplied together and added together, divided by the difference between what we observed squared summed together. And if I were that type of person, they gave you a data set of like, I don't know, 10, 15 variables and gave you X values and gave you Y values, you could sit down and do this, right? Because it would be really easy. So you have Y and you have X. And then what do you need to figure out? The mean of them. So you need a Y bar, and you need an X bar. And then what do you do? Well, your first one is X minus X bar. Your next one is Y minus Y bar. You know, you've also got this X minus X bar squared. You've got that, and the last one you've got is X minus X bar and Y minus Y bar. I ran out of room, but you need to multiply them together. And then you just have two sums here. Right? You could do that, and it'll give you a value of B. Because this is just bucket on the floor. Right? The only operations in here, PEMDAS, parentheses, you do those first. Exponents, you got one down there at the bottom, you do that one. Multiplication and division, yep, you've got some of that. Addition and subtraction, yep, you've got that too. You just do it in its order.
And this would essentially give us a 38.5?
That, no, because the 38.5 is the mean, and what are we looking for? And what was beta in that guess that we just had? It was the slope, right? We guessed it was 1. Right? We're going to find out if that's true or not. And then to find the intercept, well, this is also not that hard. Beta 1 times the mean of X subtracted from the mean of Y. Again, you could do that, right? Because we already know what Y hat is. that was 38.5, minus our beta 1, which we thought was 1, times x1, and that's going to be your intercept. I'm guessing that, again, under this completely made up numbers that I have. Man, it should be -2. Whatever. Heaven forbid this actually works, right? This part works. You know, me making this stuff up on the fly, not all the time. All right, but you got that, right? That's not hard. It's easy multiplication. All we're doing, and this is where that idea of least squares comes in, is we're trying to fit the line that has the smallest gaps. So here's an example, right? Here's one of these data points right here. Here's one of these data points right here. Our line would say that it should actually be down here at this spot. Because, you know, alpha or y equals beta times plus beta 1 plus, yeah, all that. Beta 0 plus beta 1x1 plus e. All right, that's the slope for this line. And as a result of that, we get y hat, right? This equation is always going to predict that the values are on the line. What we've got, though, is we've got a gap. We have explained this much of y's age. And what is that explanation? No, before that. If I'm explaining a woman's age based upon her husband's age, how much of the guess is explained by what? No? The husband's age, right? Okay. This, where the woman's age actually is, this distance here is unexplained. Where in the equation is the unexplained? Yes. So the gap between the line and what you observed is your error. And that's why we put the e in the equation. Because for some values, you're going to have a gap. Okay. Why was this really important? Right? Why did this change sort of the path of how we predict? Well, what Lagrange came up with was a method to get these errors really, really small. Okay. So that when you're drawing the line, you are drawing the line that has the least amount of errors possible. That's why the e is in the equation. Because we acknowledge that our dependent variables aren't determined. Listen, there's some strange people out there in the world. There was a show, they actually made a show of this, that showed, and I can't remember the obnoxious title of it, but it was something like I Love Grannies. And they would take men of Joey's age and show them in their relationship of people that are your Nana's age. And people watched this. Not too many that made a regular series out of it, but it was like one of these, TLC specials. And it was like, I love grannies. True. Yeah. And you would look at it and you would go, no, I do not enjoy this. Right? Everybody would get a little judgy. And go, no, that's not for me. You stay off my Nana. Okay? That is because life is stochastic. Okay? Because there's just that little bit of randomness out there that some dude is going to be the outlier in our scatter plot cloud of ages. It's going to happen. There's going to be people out there that are way off the line. Okay? So when you look at this cloud, you can't find one perfect line because there are some people like this dot here that's off the line. Yeah, I'm going to leave the old people alone. Right? Who are these people? Right? These people are outside of the line. If it were perfectly determined, we should have, let's see, here's 35, 35, here's 40, 40, here's 45, 45. This is where you wish you had a ruler. Okay, if it were perfectly determined, none of these dots would be off the line. You'll also notice that, well, let's see. You'll notice that there's a trend, right? Are most of the dots above the line or below the line? What does that kind of mean for us? Right, it's this theory that men, when they marry, they tend to marry younger, right? And that's why a lot of the dots are under the line. So what we do is we use ordinary least squares regression and we say, all right, how can we draw the line so that we can capture all of these differences? Well, the y-intercept, the constant, captures the fact that this line is not going to be perfect and it probably needs to be, knocked down a couple of years. Right? We probably kind of need the line down here rather than way up here. In fact, it requires that the line be knocked down. Because there's one more kind of magical thing about ordinary least squares. If we do it right, all of the errors will cancel out. So this gap up here will be canceled out by a gap down here. And that's why the E is 0. So we don't assume that there aren't any errors. We just assume that because we have a large enough sample, because we've drawn the line very precisely, because we've taken into account the y-intercept, that the line will be equidistant between the ones where the wives are older and the ones where the wives are younger. So there's a little bit of magic going on here. But it's all in how they actually constructed this. Okay? Where we're trying to get the errors, right? We're looking at the differences when we determine what the slope is. Okay. I'm going to end there. We have our introduction to ordinary least squares and how magical it can be.